Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at another question on real analysis. Is basically on sequences and on sequences, on real sequences. The question reads: suppose that s of 0 and a are positive numbers, but for all n greater or equal to 0, this is a relationship between s of n plus 1, s of n, and the number a. First question says we should show that s of n plus 1 is greater or equal to the square root of a for all n greater or equal to 0. Second question says show that s of n plus 1 is less than or equal to s of n for all n greater or equal to 1. And the last question says show that s of s equal to the limit as n tends to infinity of s of n exists. Alright, so let us start straight away with the solution. So for the first part of the equation, let's begin by showing that s of n plus 1. So let's go to a. So we are showing that s of n plus 1 is greater or equal to the square root of a for all n greater or equal to 0. Alright, so with that, it is always very difficult to prove things like this, okay, when you have the square root. So it is better to remove the square. So I'm just going to write down the statement to prove that s of n plus 1 is greater or equal to the square root of a. It is sufficient to show that I can square both sides. Okay, if I square both sides, since the s of n is positive and a is also positive and the square root of a is also positive, we can square both sides. So if we are able to show that s of n plus 1 all squared is greater or equal to a, we have just squared both sides for all n greater or equal to 1, sorry, for all n greater or equal to 0, then we have proven. Alright, now it is also difficult to show this. Okay, it is also difficult to show this, but if we are also, which implies that if we are now able to compare the difference between the square of s of n plus 1 and a, if we compare with 0, then it's going to be better. So I started by squaring both sides, then subtracting a on both sides, so that I just look for this, and then I just look for the sign. Greater than 0 means that you are positive. So it is a little bit difficult to compare two things, but I can compare something with 0, alright, because I know that if you are bigger than 0, you are positive. If you are less than 0, you are negative. Okay, so now let us look for s of n plus 1 all squared. We're given a relationship between s of n plus 1 and a. So if this is s of n plus 1, if I square both sides, it means that s of n plus 1 all squared will be equal to, I will square this, then I'm going to square this. We have to square it. Alright, so let us now simplify carefully. So we have 1/4 into, now if we square this quantity, is just the same as multiplying it with itself. So let's just multiply it with itself. When we multiply s of n with s of n, we get s of n squared. Alright, now when we multiply s of n with a over s of n, we just get a, because the s of n's cancel, we get a. Now when we multiply a on s of n times s of n, we still get a. And then when we multiply a on s of n with a on s of n, we simply get a squared on s of n, all that squared. Okay, so if I write down this as s of n squared plus 2a plus a squared divided by s of n squared. Alright, so it therefore means that if we now get a difference, that is s of n plus 1 all squared minus a, we are going to get, because now we need to get this difference, right? We are going to get all of these, because this is s of n plus 1 all squared, then minus a. All right, so if we multiply 1/4 with s of n squared, we just get s of n squared on 4. If you multiply if you multiply 1/4 with 2a, we just get a divided by 2 plus a divided by 2. If you multiply this with 1/4, okay, we get or in fact, rather than doing this, let's just factorize 1/4. When we factorize 1/4 from this term, we just get what is here, okay, just get what is there. Then when we factorize 1/4 from a, we get minus 4a. That's since the minus sign is there. You realize that if I multiply 1/4 and the 4a, I just get a. Now if we bring like terms together, we are going to have a negative sign here, because 2a minus 4a gives us negative 2a. Okay, now from here, if we carefully simplify, we have the 1/4 outside. Now the LCM is simply s of n squared, okay, s of n squared. Now when we multiply s of n squared with this, because this is the same as kind of divided by 1, and also this is divided by 1, so when we get the LCM, we need to divide by 1 and multiply by this. We are just going to get s of n raised to the power 4 minus 2a times s of n squared, then plus a squared. That is what we have. All right, so my instinct tells me that this is kind of a perfect square. In fact, if you look at it directly, you realize that you have something like 1/4 s of n squared. Okay, we multiply it with let me just write all of this. So now I don't know if you can realize this, but I have just realized that what is inside the bracket is a perfect square. That is, this term here, that is what is here, okay, is just equal to s of n squared minus a, all that squared, if you complete the square. All right, if you complete the square, you're going to, in fact, if you expand this, you're going to arrive here. All right, so let's now conclude. So this therefore means that this means that s of n plus 1 all squared minus a is equal to this quantity. All right, it's equal to this quantity. Okay, now we can even write this denominator as 2 times s of n, all that squared. Okay, and then we now use the laws of indices. Since we are taking something squared divided by something squared, we could just divide the two quantities and then we square. So I could just take my denominator as 2 times s of n and my numerator as s of n squared minus a. So you realize that since this is something squared, then it is always greater or equal to 0, right? Since the numerator could be 0, that is if s of n is equal to plus or minus the square root of a, then the numerator is going to give us 0. All right, in fact, we are just saying that whenever you square any quantity, the result is always greater than 0, and the result could also be equal to 0 if that quantity is 0. And for this quantity to be 0, it suffices that the numerator is 0, and that is a possibility. So we have just proven that. So this now means that s of n plus 1 all squared minus a is greater or equal to 0. Now to get the proof, we are going to add a to both sides of the equation. So we get s of n plus 1 all squared is greater or equal to a. Then now we just take the square root on both sides of the equation. All right, if we take the square root, of s of n plus 1 all squared, we are going to have greater or equal to the square root of a. But now the square root of s of n plus 1 all squared is the absolute value of s of n plus 1. So we have the absolute value of s of n plus 1 greater or equal to the square root of a. But since s of n plus 1 is already positive, then its absolute value will just give you the function itself, the sequence itself, s of n plus 1 greater or equal to the square root of a. And we are done with the proof of the first part. Alright, let us move on to proving the second part of the equation. So the second part says we should show that s of n plus 1 is always less than or equal to s of n. So B, we are showing that s of n plus 1 is always greater or equal to s of n, or it's always less than or equal to s of n. So we begin with what we know about s of n plus 1. Okay, this is s of n plus 1 that we have here. So s of n plus 1, s of n plus 1 equal to this. Okay, so if I subtract s of n on both sides, it means that s of n plus 1 minus s of n will be equal to this quantity minus s of n. I'm just subtracting s of n on both sides, so which will be equal to, now if I multiply by half, I get half s of n plus half, in fact let's just factorize half, so we get s of n, so we get s of n plus a divided by s of n. If we factorize half from s of n, we get the minus 2 s of n. We did this before when we were factorizing 1/4. Alright, so we have half into the LCM is in fact, if you bring like terms together, first of all we have s of n minus 2 s of n is just negative s of n. So I'm going to start by writing the positive term before I subtract the s of n. Alright, so from here we can write half, the LCM is simply s of n, s of n. Now the numerator is going to give us a minus s of n, all that squared. That's what we have after simplifying. Okay, but now we know that, what do we know? Because we need to look for the sign of this. Okay, we need to look for the sign, because it's very difficult, like I said, to show that s of n plus 1 is less than s of n. But if we are able to show that s of n plus 1 minus s of n is less than 0, then everything is going to be fine. So we have already seen previously that s of n plus 1 is greater or equal to the square root of a. Okay, this now means that s of n, that is, wait, let's first of all say for all n greater or equal to 0. So if I want to change s of n plus 1 to s of n, it's also going to be greater or equal to a. But now we are going to begin with for all n we are going to have for all n greater or equal to 1. Why? Because in the first scenario, if n is 0, we have s1 is greater or equal to the square root of a. In the second scenario, we cannot begin with n equal to 0 again. Okay, we are instead going to begin with what? N equal to 1, right? So that we should also have s1 greater or equal to a. All right, just to respect the proof. So it means that s of n is greater or equal to a. Okay, so if s of n is greater or equal to a, and I know that s of n is a positive sequence, I can square both sides. If I square both sides, I'm going to have s of n squared greater or equal to a. Now this means that if I subtract s of n on both sides, s of n squared on both sides, I'm going to have 0 greater or equal to a minus s of n squared. Now if 0 is greater than something, it means that that thing is less than 0. So it means that a minus s of n squared is what? Greater, no, it's less than or equal to 0, since 0 is greater or equal to it. So 0 is greater or equal to it, it means that it is less than or equal to 0, and less than or equal to 0 means that you are negative. All right, now we have seen that the numerator is negative, the denominator is s of n, which is a positive sequence. Okay, so we have negative divided by positive is negative, times positive is still negative. So we can conclude that since s of n is positive, then we have that our s of n plus 1 minus s of n will be less than or equal to 0. Why? I've just explained. The numerator is less than or equal to 0 and the denominator cannot be 0. So whenever you take positive and you divide with negative, it gives you negative. And since the numerator could be 0, then that's why we are precising that it's less than or equal to 0. So if we are able to add s of n on both sides, we are just going to get s of n plus 1 less than or equal to s of n as required. So that's what we require to show. Now let's round up with the equation. The last part of the equation is saying that we should show that the limit of the sequence s of n exists. Okay, so how do we show that the limit of a sequence exists? In fact, it is bizarre to actually show that the limit of the sequence exists, maybe using the epsilon delta definition of the sequence. In this case, this is a recursive sequence. So we just need to use the fact that if a sequence converges, then its limit exists. So if a sequence, and vice versa, so if a sequence converges, comma, then its limit exists. Now, when do we say this type of sequence converges? We should also know that if a sequence is monotonic and bounded, then it converges. Okay, so in this case we have to justify that since s of n plus 1 is less than or equal to s of n, in fact we are saying that s of n plus 1 minus s of n is less than or equal to 0. That's what we are saying. So since that happens, we can say that the sequence s of n is monotonic, and it is definitely monotonic decreasing. Okay, so monotonic, it is monotonic. In fact, let's just precise that it's monotonic decreasing. Alright, now is it bounded? Yes, it is bounded, because it is basically bounded from below. Since we showed in the first question that s of n plus 1 is less than, is greater or equal to the square root of a, it therefore means that if I introduce a sequence s of n, it will be still greater or equal to the square root of a. Okay, so it means that the square root of a is what? Less than or equal to the sequence s of n. So which means that it is lower bounded by the square root of a. So it clearly converges. Okay, so it converges because it is monotonic decreasing and lower bounded. We have no idea about its upper bound. Okay, we have no idea about the upper bound. I don't know if we could find the upper bound, but it's not really necessary in this question. But we have seen that it is monotonic decreasing, so we have to specify, because if it was monotonic increasing and lower bounded, we cannot conclude. Okay, we could conclude provided we have the upper bound, but since it is monotonic decreasing and it is lower bounded by the square root of a, then it converges, and if it converges, then its limit exists. So we are done with the equation. Alright, thank you for watching. Make sure you like, share, subscribe to the channel, and share the video with your friends. See you in the next video.